we've been using f prime of x for the derivative function, and that's probably the one that we'll use the most often in this class. But there are other notations for this, and sometimes it's more useful to use the other notations. It might be easier to remember certain rules with the other notations for some people. So you use whichever notation you like the best, as long as it's correct. That's how, and I go back and forth. So you have to know them both, because I just go back and forth. So when I say both, there's more than two, but the main two, right? So sometimes they'll give you y equals something. So then the derivative, you can write y prime for the derivative. And also, in physics, they often use a dot. But in physics, they'll often use t. You'll have x of t, for example, x of t or y of t, where this is a position, and t is the independent variable. So often when you're taking the derivative with respect to t, in physics, they'll use like a dot on top of x. I won't use that. I don't care if you use that. But the dot on top of x is something that you might see in physics. The main other notation that you'll see here is Leibniz notation. And what that comes from is, of course, it's Leibniz's. So Newton used the prime, I guess, and Leibniz used the ddx. So the idea was this. Remember, we talked about rate of change. So rate of change, it was delta y over delta x, right? The rate of change of y with respect to x. So this would have been the average rate of change. So this would have been y2 minus y1 over x2 minus x1. We talked about this very briefly. Rate of change of y with respect to x. But then when we want to go, so this will be the average rate of change. And then if you want to go to the instantaneous rate of change, you would take this guy, which often we talk about like delta t. We take this guy to 0, right? So instantaneous rate of change, I'm just going to write ROC instead of rate of change, would be the limit as delta x goes to 0 of delta y over delta x. So that's the reason for the notation. In the limit, the delta goes to a regular d. So it goes from the Greek d to sort of a regular d, little d. Okay, so then this became the notation for the derivative. So if you see dy dx, it's the same as y prime, or f prime of x. This is technically not a fraction. So it's defined as this limit, but talking about dy and dx don't make sense right now. Later on, we'll kind of make some sense of it, and so that we can use it in different ways. But for right now, especially, don't think of this as a fraction, even though sometimes you can kind of use some fraction stuff to remember stuff, which is why it can be useful. Okay, so that's dy dx. Sometimes you also see df dx, if we're talking about a function being y instead of x. Another one which we won't see very often here in this class is just a big D. So df. One that you won't see very often either, even in Calc 3, though you might see dxf means the derivative with respect to x. This you see if this f has like x, y, and z, and that's what I'm saying in Calc 3. But these more like operator type notations, you probably won't see until like if you're taking like PDEs or something much later on, partial differential equations. In general, in calculus, I like really never use these. I use most often this guy and this guy. So there is that. All right. So now that we're talking about that, other notations, the other last thing I wanted to mention in passing is second derivatives, third derivatives. So higher order derivatives, right? I can take the derivative once, and if I have a function, well, I can take the derivative of that function again. So second derivative, right? So it basically means I take the derivative twice. Okay, so let me say, I'm not going to ask you to do this before the test on Friday because, I mean, it takes enough time to take the derivative once when you're using the definition of the derivative. Now, when we start using the derivative rules and we do it fast, then we start taking the second derivative, talking about the second derivative, third derivative, all that stuff. So mostly this is just a little bit of background. We'll return to it right after the test, but I'm not going to have you take second derivatives on this week's test. For sure, no way. Okay, take the derivative twice. Now, since I'm talking about notations, I better explain to you what the notation is for the second derivative. You put two little primes, right? So then it would be y prime. Now, when it comes to dy dx, you don't want to do dy dx squared because then you might just be taking the derivative and squaring it. So the 2's are staggered. So it's dy squared d squared y dx squared. If I have an f, it's the same. Here, you might see that, or you might see something like this. Okay, but again, whoops, 2 primes, right? 2 primes. 2 primes or d squared y dx squared. So those are the ones that we're likely to use. Now, of course, third derivative, then you have 3 primes. Fourth derivative, you have 4 primes. This is getting onerous with the primes at this point. So some people use a like a Roman IV. More often, we just start using like a 4. But to make sure that it's clear that it's the fourth derivative and not f of x to the 4th power, when you use a number, you always put it in parentheses so that we know that it's the 4th derivative. So hence, if I'm talking about the nth derivative, I have an n up there. So this is the nth derivative. And if I want to write that in Leibniz notation, I would write d n y dxn. Okay. Oh, I forgot this. For the Leibniz notation, right? So if I have ordinary f of x, if I want to, or f prime of x, if I want to do f prime at x equals 2, I'll put it there. So with the Leibniz notation, there's no place to stick in the 2. So you would do a bar and you put this, you would read it as dy dx evaluated at x equals 2. Okay? So that's why in this class a lot we use this notation because it's simply faster to write, especially when you're evaluating at a point. But sometimes you'll see where we use that when it's kind of easier or helps us in some way. Sorry, I forgot that when we were talking about it. And I think that basically covers it because we got the nth derivative. Oh, I did need to mention the physics type problems. And I'll talk about it with the notation that we use here because we don't use the dot, right? So remember we've got if S of t is a position, and this is simply one-dimensional motion, the position at some time t of your particle, and then we said, so the derivative S prime of t is the, let me just write it this way, velocity is the derivative S prime of t. So you might also, with Leibniz notation, you would write ds dt. So this is the velocity function, right? And then the derivative of the velocity is acceleration, right? Because this is change in position over change in time, and acceleration is the change in velocity over the change in time. So acceleration is the first derivative of velocity. It's the second derivative of position. Okay, so you can do d squared s dt squared if you want to use that. And this is the acceleration, which I think only has one c. Whatever, I spelled it wrong. It's one c or one l. And then if you want to talk about the third derivative, which we almost never do here, but you might talk about it in physics, third derivative is actually called jerk, right? Because it's change in acceleration over change in time. And of course, if you are driving and your acceleration changes quickly, you feel a jerk, like if you slam on the brakes because some idiot pulls their car in front of you. You know, these things happen.